Welcome to section 6.1. This is a big moment in the class. We're really starting to do what most people would call traditional statistics. And so we're going to develop over the next 3 or 4 videos two big ideas for the semester. And big idea number 1 is the idea of a confidence interval, and that's going to be chapter 6. And then big idea number 2 is that of a hypothesis test, and that's going to be chapter 7. Okay. What's the goal for each of these? The goal for each of these is this picture that I've drawn over and over again, and it's the fact that we have a sample on one side and we have a population on the other side. The population is usually what we want to know information about, but the question is, what can the sample tell us about the population? And then when we do a hypothesis test, we're going to go backwards. We're going to say we know something about the population. What should we expect the sample to look like? So what we've got is we have a sample. For our case, it's going to be X bar, which is the average, and population is going to have mu, which also means the average. They both mean average, but they mean average in a different context. This is the average of the people you're studying. This is the average of everyone everywhere. And the question we're going to ask for confidence intervals is, if I know this, how can I guess what this is? So how can I start by knowing the average from 500 people and use that to make a pretty good guess for the average for everybody? And this is at the heart of what a statistics is and the heart of a confidence interval. All right, we have a few words to throw at you at the very beginning. The first word is what we call a target parameter, and the target parameter is the property of the population we want to know. So for our example, the target parameter for today, and really for most of the semester, the target parameter is going to be mu. So the target parameter is, what is that actual average for the whole population? The point estimator is the value. Okay, so the point estimator is what we calculate from the sample. So it is the calculated value from the sample that we use. So if our target estimator is mu, our point estimator is going to be X bar. So in other words, the target estimator is the average of the entire population. We don't know that. What we do know is the average from the sample. And so that average is going to be what we're going to use to estimate this target parameter. And what we're going to do is, instead of making an exact estimate, we're going to make a range of values. A range of values which likely contain, I ran out of space, which likely contain, I'm doing awful, which likely contain mu. So our interval estimator, what we're going to have is we're going to have some sort of starting value, and then we'll have some sort of number here. So let's just do an example, like the number 5 and then the number 10. So we'll end up with an interval that begins with 5 and ends with 10, and that means that our target parameter, the average that we're looking for, is likely within this range. And the point estimator is always going to be smack in the middle. So if we're 5 to 10, the point estimator is going to be 7.5. So what we're going to do is we're going to make a little window of values, and we say, we don't know. So if you, say, go around and find an average of something, and you find that the average is 7.5, that doesn't mean that the true average for the entire population is 7.5. But what you can do is you can make a window of values around that average from 5 to 10, and that window has a really good chance of containing mu. So this is the big idea of a confidence interval. The goal is to create this range that is likely to have mu inside of it. Okay, so before we do this, we need to introduce an idea, and the idea is one of a critical value. And so a critical value, really simply, is just a value on a normal distribution. So if I have a normal distribution that looks like this, the critical value is the value right here, that if I put negative value on this side, then I get whatever percentage I want in the middle. So it is the value, the values on the normal distribution, the values on the standard normal, that give the desired probability. I'm not doing a great job writing my sentences today. In the middle. Now, what's going to happen is that critical value is going to depend upon the problem. So some problems we might say, I want a 90% critical value, and a 90% critical value would mean that we want to make the middle window here have 90% to it. We may ask for a 95% critical value. If that's the case, then we're going to try to make that middle window have 95% in it. So what I want you all to do, and we've done this activity in class, but it's been a little while. So what I want you to do is figure out what is that critical value. What is that critical value, ZC, that makes this window in here 90%? And so now is a good time. Try pausing your screen, grab your calculator or your app or your Excel, and see if you can figure out what value do I need to make that window in the middle 90%. All right, hopefully you paused and hopefully you gave it a chance. What do we need to do? We need to grab one of those three. You need to grab your calculator. If you're on your calculator, you're going to use the command called inverse norm, because the normal distribution, you tell it the range and it tells you the probability. Inverse norm does that backwards. And again, we talked about this in class just briefly before the break, but I know that feels like a really, really long time ago. If you're on Excel, then we're going to use see, I think, oh, I don't remember the command off the top of my head. I think it's norm.inv, maybe? Or is it inverse.norm distribution? I don't remember. I shouldn't write that down. If you start typing things like inverse and norm, you'll figure the right one out. But what I'm going to do is I'm going to use the app, because I think the app is the one that's going to be the easiest for us to make sense of right here. Okay, so here's my app. And what I want to do is I want to figure out what window in the middle do I need to get a 90% range. It's a standard normal, so that means I want my mu to equal 0 and my standard deviation to equal 1, not 11, 1, okay? And so that gives me my standard normal. Now, I want to come over here to the probability side because I want to tell it a 90% probability and figure out what number to put on here. But I want you to notice something. If I put 90%, the calculator is not going to give me the right answer. Oh, I can't put 90. I need to do 0.9. If I do 0.90%, the calculator is going to mess up for a few things. First, I can either choose the right or the left, but neither of those are going to give me the right answer. Let's make this 0.9 again. 0.9. Notice this gives me 90%, but notice that doesn't mean the middle is 90%. It means all the way to the left is 90%. So the picture that I had looked like this. The picture that I had all of this 90%. But that's not what I want. So what I need to do is I need to figure out how much extra area falls over here. And the answer is I've got 5% and 5%. So instead of putting 0.9 in my problem, what I want to put is I want to put 0.95. Because now if I have 0.95, I have 5% on this side, 5% on this side, and 90% in the middle. And so what I see is that the appropriate range is the range 1.644. 1.64 is the appropriate number here, and this number is just going to be negative 1.64. So that's how we find the critical value. You use the less than, and you put the percentage, but don't put the 90%, put 95% because you have to add the amount that's on this tail over here on this side. Okay, once we are able to find a critical value, and we will do more of these, so don't worry about that. Once we are able to find these critical values, that lets us talk about what we want for our confidence interval. So our confidence interval is just the range. Our confidence interval is just a range that makes it where the probability of our thing being between, say, A and B is equal to 90%. So if I want a 90% confidence interval, then I want a range of values that makes that equal to 90%. Now what I'm going to do is I'm going to recognize that if I write this as a ZC and a positive ZC and make this a Z value in the middle, then I can do the problem just like I did a moment ago with the confidence interval. So I'm going to do a little bit of deriving. This is going to be a little mathy, and I know that this idea here is a little theoretical, but just hold on. In just a few minutes, we're going to have a formula that you can work for. Don't fast forward. Listen to it, and just let it soak in and appreciate how to do this math. So what we want is we want the range between ZC and negative ZC to equal 90%. And so we want to figure out which values of X make that 90%. Well, what we know is we know that Z is equal to X minus mu over sigma. This is our Z-score problem. But because we have a sample, this X is an X bar, and this sigma is divided by the square root of n, since we have more than one item. If we had n items, this becomes our average, and this becomes, we divide by the square root of n to get our new standard deviation. That was the class from the other day. This is the central limit theorem. So what I'm going to do is I'm going to write that z-score term here in the middle, and have ZC and negative ZC, and then I'm going to do some math. I'm going to solve for mu so that I get mu right in the middle. Okay? Now, what I'm going to do to solve for mu, the first thing I'm going to do is I'm going to multiply everything by the denominator. So I'm going to multiply by sigma over square root of n, multiply by sigma over square root of n, and multiply by sigma over square root of n. And that's going to give me my first term. So my first term is ZC times sigma over square root of n is greater than x bar minus mu is greater than negative ZC times sigma over square root of n. Now, the next thing I'm going to do, I'm solving for mu. So the next thing I'm going to do is I'm going to subtract x bar, but I have to subtract it off of everything. And I'm going to write the x bars first because that's what I'm used to, and it looks a little bit nicer that way. So I'm going to do minus x bar plus ZC times sigma over square root of n is greater than negative mu is greater than negative x bar minus ZC times sigma over square root of n. Notice this had the negative sign attached to it. Okay. Now I'm ready for the very last part of this problem, and that is, well, I have a negative, so let's just multiply everything times negative 1. So just multiply everything times negative 1. That means I have to multiply the whole sections times negative 1. And so everything changes sign. So this first part changes sign to be x bar minus ZC times sigma over square root of n. This part becomes a mu, and this part becomes x bar plus ZC times sigma over square root of n. And when you multiply by negative signs, you might remember your inequality changes directions. Now this ends up being the formula that we're going to use for confidence intervals. So if you didn't follow any of that, you can keep this confidence interval formula in front of you, and you will be just fine, and everything will work out just fine with that formula. Okay, so now that we have the confidence interval formula, we have a question that is, well, what does this represent? And I already kind of pointed at this, but let's go through one more time. Just what does this represent? Well, we're going to get, when we're done with the confidence interval, we're going to get a number. And so we're going to have some number on this side and some number on this side. And what we're going to have is some sort of range of values with a number over here and a number over here. And right in the middle is going to be whatever that x bar term is. And so over here is going to be x bar minus ZC times sigma over square root of n. And over here is going to be x bar plus ZC times sigma over the square root of n. And what that means is that if someone asked, where is mu? Where is mu? Well, the answer is mu is most likely somewhere in this collection of values. So if we do a problem, and we'll do a problem in just a little bit, but if you did a problem and you got, say, 5 to be this lower number and 10 to be this little number and 7.5 to be the number in the middle, and someone asks, what's the real average? And you would say, the real average is between 5 and 10. And then the next person person might say, well, how confident are you that you're right? And you'd say, I'm 90% confident. And that means if I were to do the same experiment over and over and over again, if I did the experiment, you did the experiment, every student in the class does the experiment, 90% of us will have mu in our range. And then 10% of us will have a range that falls either too small or too big and misses the real average. But most of us will have mu somewhere in the middle of this. So that's the question we're asking when we create a confidence interval. Where is mu? And the answer is there's a 90% probability mu is between 5 and 10, or between this number and this number. Now what you'll notice is that the width of this, so if I were to come here and look from here to here to here, this width right here happens to be that term that gets added on. That happens to be the ZC times sigma over square root of n number. And we call this number the error. And that means if you start at x bar, that's how far you can move over and still be within your window. And that's how far you can move over to the left and still be in the window. So this is often called the error term. And then you see we have our point estimator right there in the middle. Okay, we are ready to try some problems. So let's do some problems and see how much success we can have. All right. Tell you what, let's keep our formula and then come work on the problem. So the first problem is problem 6.2. Part A. A military company knows that the weight of members of the military is normally distributed with a standard deviation of 20 pounds. Before an operation, 40 individuals are weighed in full gear. Their average weight is found to be 235 pounds. Find a 90% confidence interval for the weight of the military member in full gear. So what do we need to do? We need to use this formula. So we need to take this formula that we have right here, and we need to figure out the different things to plug into it. So what do we need to plug in? Well, we need to plug in x bar. We need to plug in sigma. We need to plug in n. And we need to plug in ZC. If I can figure out these 4 numbers, then I can plug in everything to my formula and have my confidence interval created. Some of these are really easy because they're just told to us in the problem. So if you read carefully, it says the members have a standard deviation of 20 pounds. So that means this standard deviation is 20 right here. It said 40 individuals. That's how many individuals. N always tells us how many people we studied. How many people, items, things. N is the size of our sample. And so that means N is 40 in this problem. Finally, whenever they studied their 40 individuals, they got the average weight to be 235. So the average, this x bar, is 235. So these 3 numbers show up right in front of us, and they're really pretty simple. Now, what about the ZC? It's tempting, but incorrect. So I'm going to write it in the wrong color. It's tempting to put like 90% for ZC. But ZC is not 90%. ZC is the number that when I draw my normal distribution makes the middle 90%. So ZC is not the 90%. ZC is that number. So let's erase that and let's pull out the app and look at it. And this is the same calculation that we did just a minute ago. Because if it's 90%, we need an extra 5% on that side. So we put 95 into our calculator, we look at the left-hand side, and we get 1.644 for our ZC. So ZC is 1.644. 1/4 is plenty. Okay, so now we're in really good shape because we have everything we need. So let's just grab our formula and start plugging stuff in. So we're going to have 235 minus 1.64 times 20 divided by the square root of 40 is less than mu is less than 235 plus 1.64 times 20 divided by the square root of 40. And what you'll notice is we always have the exact same thing written down on both sides, except one side we subtracted and the other side we added. So it's the same thing on both sides. Okay, now I just have to type these into my calculator. Be a little bit careful when you type them in your calculator. If you do 235 minus 1.64 and hit enter, then that will do the subtraction first. But we don't want to do the subtraction first because we need to follow the order of operations. So we need to divide and multiply first. So I'm going to do 1.64 times 20 divided by the square root of 40. And I know you all will probably have different calculators than me, but that's fine. So that gives me 5.18 for that number. And what if I just go ahead and write this out, I think? Maybe 235 minus 5.18. And then this side is plus 5.18. Oh, 18. You don't have to write these out, but it might make your life a little bit easier. So let's do 235 minus 5.18. And that's going to give me 229.82. Is less than mu, and then on the other side I just have to switch it to a plus sign and I get 240.18. So what is the information does this tell us? This tells us that if somebody said, what is the average what is the average of a military member? We have all these members, we've measured 40 of them. They say, okay, what's an average size? I would say that an average size is somewhere between 229.82 and 240.18. So your head officer, the general, comes up and says, hey, what's an average size? I need to put a whole bunch of these people on an airplane. I need to know the average weight so that our airplane is weighed down correctly. You could say the average weight will be between 229 and 240. And then if that member says, how confident are you in this? And you can say, I'm 90% confident. So I know that there is a 90% probability that the number falls within that range. Okay, what we want to do now is I want to change the question ever so slightly on problem B. And problem B says, what if instead of doing a 90% confidence interval, we did a 99% confidence interval? And I want to ask a question. I want you to think about it before you do any calculations. So when we're at 90% confidence interval, we had the numbers 229.82 and 240.18. My question is, which is going to be the case? When we go to 99%, is that going to make the interval wider than it was the first time? Or is that going to make the interval skinnier than it was the first time? So do you think you're going to have a bigger range of values when you switch from 90 to 99%? Or are you going to have a smaller range of values when you switch from 90 to 99%? Pause real quick. I want you to actually think about this. I want you to consider which one you think is the right answer. Okay, well, let's hold on, and I'm not going to tell you the answer right away. Let's go do our calculation and see what we come up with. Okay, so if we're going to do this problem, everything stays the same. The x bar is the same, the sigma is the same, the n is the same, and the ZC is the same. And so the only thing left is to add, the only thing that changes, sorry, the ZC is not the same. The x bar, sigma, and n all do stay the same. So what is the ZC? The ZC, I take my picture, and now I put ZC here, and now the difference is I need 99% in the middle. So now what is this extra little sliver over here? This extra little sliver is a 0.5%. So what do I want to put in my calculator? In my calculator, I want to use x, or I want to use my probability I don't want to use 99%. I want to do 0.995 in my probability because I need to pick up that extra 0.5%. So I need that extra 0.5. So I'll come over here to my problem. I'll put 0.995 and I'll hit enter. And I'm going to get 2.57 or 2.58 for my answer. Let's go 2.58. How about that? Okay. So there's our 2.58. Let's look and see how that changes this problem. So when I come over here and start calculating, that means this 1.64 changed to 2.58. This 1.64 changed to 2.58. And that means that number changed, and it will make that number change. Let's calculate those out. So now I'm going to do 2.58 times 20 divided by the square root of 40. And I'm going to get 8.15 or 8.15 sounds good. And then I'm going to add and subtract that on there. 235 minus 8.15. And I get 226.85 on that side. And then on the other side, I get the same thing but with a plus sign. And I got 243.15 on the other side. So now my numbers are 226 and 243. So what numbers did I get? I got a wider range of values. So my wider range of values was now 226.85 to 243.15. So if you said 99% makes the interval wider, congratulations, you're right. If you didn't, hey, this is a great opportunity to learn. So let's stop and think about why this should be the case. It feels a little counterintuitive, doesn't it? I think our gut says a bigger percent should make it smaller because we're more confident. But notice, we are to become more confident that you have trapped mu, you need a larger range of values because we're saying, how confident are you that mu is inside of this interval? Well, I'm more confident that mu is in here than in here because there's space, because this traps a larger set of values than those set of values. So the bigger your confidence interval gets, the bigger your confidence gets, the wider your intervals become because you are more and more likely to have mu inside your interval the wider it gets. Okay, so it feels a little counterintuitive, but hopefully it makes a little bit of sense. All right, let's jump over to part C and see what happens when we get part C. Part C is the same problem, except now we're going to switch it from 40 individuals to 400 individuals. So let's do the same thing again. So come here, and up here we had 40 people. We had 40 people. And then I want you to ask yourself the question, what happens when we move to 400? Does our confidence interval get wider, or does the confidence interval get narrower? What's the case? Are we going to get bigger numbers than these or smaller numbers when we add more people to our sample? All right, again, you might want to pause, take just a second and think about it. Okay, great. I hope that you have some intuition, and we will see how it goes. So what are my new numbers? Well, I'm at 90%, so I'm back to that 1.64 value here, but now I'm at 400 instead of 20. So let's come and do this problem again. These are, let's erase these. I'm trying to keep some of these things. Maybe this is fun. All right. So we're back to that original problem where we had 1.64 right here. 1.64 because we're back to a 90% confidence interval. And now the difference is, instead of 40, we've made this 400. And so let's look and see what happens. So now we do 1.64 times 20 divided by the square root of 400. And that's going to give me just 1.64 as my result. Oh, I guess that makes sense, doesn't it? Because 400 is 20 squared. So square root of that cancels. Okay, so that gives us 1.64 on both sides. So now let's do 235 minus 1.64. And that's going to give me 233.36. Now if I do the same thing with the plus sign, I get 236.64. So these are my new numbers. My new numbers are 233.36 and 236.64. So what was the result? How did these numbers compare? Well, 233 and 236, those are closer together than those values. So the answer was that it got narrower. So the answer was 233.36 and 236.64. So it got narrower. And if you think about it, that kind of makes sense, doesn't it? The more people, if we're trying to use X bar to guess at what mu is, the more people you have in your sample, the more confident you are, the more you've narrowed down what mu actually is. So you have a better picture of what the real average is, the larger your sample is. So if you had 4 million people and weighed them, then you would really know that average really close. You'd be like right on top of it. Okay, so the larger your sample gets, the narrower your confidence interval gets. All right, we have two final thoughts. Thought number one is, what sample size? Well, there's a standard, and the standard is we need one of two things. Either we need to know that the distribution is normal already, which is usually not the case. Often we kind of know it's mound shape, but even if we do things like weights or heights, these are kind of normal shape, but we don't know it's exactly normal. So you need to either know that it's normal or have n at least 30. There's nothing magic that happens at the number 30. It's just that this is a number that statisticians have said by the time you get to 30 people in your sample, we're pretty confident that the shape has taken that normal shape, because we know from the central limit theorem, the bigger and bigger n gets, the more it takes that bell shape, that normal shape. So what do you need? You need to either start off with a normal distribution or have n at least 30. Finally, I have a confession, and that is that everything I've told you for this entire video is a lie. The reason is, when we look at all these formulas, and especially when we look at this formula right here that we've been using the whole time, notice what we've made one big assumption, and that is we assume that we know what sigma is. If you go back and remember, sigma is the standard deviation. This is the standard deviation of the whole population. So if we're to figure out the standard deviation of the whole population, how could we do that without actually knowing what the average of the population is? So usually you must know mu before you can figure out what sigma is. So it turns out that really none of these calculations we did today are all practical, because in general it's impossible to know sigma. We rarely, and when I say rarely, I mean basically never. I can't imagine any situation. We rarely know what sigma is. So we have to make an alteration, and that's going to be the next section. The reason why we teach this, even though it's not real practical, is this is a great place to familiarize yourself with the math, a great place to familiarize yourself with the type of thing it takes to create a confidence interval, and then we'll make a couple small adjustments next time. The big adjustment is going to be, instead of using sigma for the population, we use S for the sample, because we can calculate the standard deviation for the sample. But when we do that, we also have to make a small change to our critical value. And so this is going to be the big idea that comes in the next section. So I look forward to seeing you then, and we will be all done.